Welcome to part 2 on applications of vectors. We're going to look at a velocity of a moving object. The velocity of a moving object is modeled by a vector whose direction is the direction of motion and whose magnitude is the speed. Because of wind, the velocity of an airplane relative to the air and the velocity of the airplane relative to the ground, true velocity, are usually different. The true velocity is represented by the vector sum of the velocity relative to the air and the velocity of the wind. So here I have these vectors in a field, and all these little blue vectors represent the wind, and this orange vector here represents a plane. It has speed that's clearly faster than the wind because the vector is longer, and it is traveling in a northwards direction. If we were to combine both the wind direction and the plane's velocity, we have the velocity of the wind and we have the velocity of the plane, and if we were to add them together, we would get this slightly off north vector that represents a little bit longer vector, but it's not moving in the correct direction anymore. It's slightly off north. So this is how we can think about different velocities of objects and how they relate to each other. In this example, a pilot heads his jet due east. So let me draw a jet in the due east direction. The jet has a speed or magnitude. I'm going to call it v sub jet. And the magnitude is equal to 425 miles per hour relative to the air. The wind is blowing due north with a speed of 40 miles per hour. So I'm going to draw another vector that represents the wind. The wind is, we'll call this the magnitude of v sub w, the wind, is equal to 40 miles per hour. If we want to try to find the true velocity of the jet as a vector, we need to figure out the sum of these two vectors, because the wind is affecting the plane's flight. Finding the sum of the vectors will be helpful, but then once we've found the sum, we need to find the magnitude, because what we're really looking for is the velocity of the jet as a vector. So we are looking for this. So if we wanted to find how long this vector is, we would take the v sub j vector and the v sub w vector and add them together. In component form, the v sub j vector plus the v sub w vector will simply be 425, 40. And from here, if we want to find the magnitude, we would take the square root of the two values squared. I've gone ahead and calculated the square root of 425 squared plus 40 squared. I've gone ahead and calculated the value for the square root of 425 squared plus 40 squared, and I get 426.878, and the decimal continues, so I'm just going to round it to a full number, 427. Miles per hour. Let's take a look at the next example. An airplane heads due north at 300 miles per hour. It experiences a 40 mile per hour crosswind. The direction is 30 degrees east of north, which means we're measuring the angle that's given, 30 degrees, off of north, and this is kind of a nautical term, and so you won't necessarily know that unless I tell you, or you've sailed. So this will be 30 degrees, and the vector for the wind is basically 60 degrees because we're measuring off the north vector, or north, true vertical, instead of off the horizontal or standard form. If we want to find the true speed and direction of the airplane, we need to draw a vector. So the plane will represent this as 300 miles per hour, and we'll represent the wind as 40 at an angle of 30 degrees. So we need to think about how we're going to describe this. If I wanted to describe this 60-degree angle here that the wind is forming, it's easy to describe the components of the plane. If we wanted to give the vector for the plane, we'll call it v sub p, is equal to 0 in the x direction, 300 in the y direction, because it's heading due north. And if we wanted to represent the vector for the wind, we would have to represent it as two pieces. Because we know the angle and we know the length of the vector, we can say that it's 40 times cosine of 60 degrees, comma, 40 times sine of 60 degrees. If I want to simplify this further, the components of this will be 40 times 1/2 and 40 times root 3 over 2. Which will simplify even further to 20, comma, 20 root 3. I'm now going to add the two vectors together. The vector that represents the plane plus the vector that represents the wind is equal to 0 plus 20, and 300 plus 20 root 3. And I'm going to leave that in exact form right now. I'm not going to actually calculate the decimal. If I wanted to find the magnitude of this vector, and remember this vector that we're looking for is technically this one right here. Let's find the magnitude, or how long this vector is. That gives me, if I want to find the magnitude, it's the square root of the first component, 20 squared, plus the quantity, 300 plus 20 root 3 squared, all under the square root. And I get I'm going to just go with approximately. I'm rounding to whole values here. 335 miles per hour. You're welcome to pause the video and check that. Now the next thing we need to figure out, we've found the magnitude, but we also need the direction. We can find the direction by using the components and the tangent function. If we know that tangent of theta is equal to y over x, we can take 300 plus 20 root 3, all divided by 20. And then if I want to find the angle theta, I take the tan inverse of that fraction, 300 plus 20 root 3, all divided by 20. And theta is equal to approximately 87 degrees. Now remember, you have to change your calculator to degree mode when you're doing this. That doesn't make really that much sense because we were measuring off of north. If we wanted to say what this was with respect to north, due north, if this is the angle that is 87 degrees off of standard position, the angle here that we're looking for is how far it is away from actual due north, which is whatever would make up the remainder to get to 90 degrees. This means that my magnitude is 335 miles per hour, and my plane is traveling at north 3 degrees east. So we would write something that looks like north 3 degrees east, but we would say that the plane is traveling 3 degrees east of north. So we're measuring off of north toward the east.